Next example, we are looking at the flow in a coating process. So imagine you have some pool of liquid, and then you somehow have this like little conveyor belt that is coating a something, wire or something, and it's moving in this direction. So it's going to entrain some flow with it, and then that some liquid with it, and that liquid is going to reach this nice steady thickness of delta over here. So we are going to focus on modeling this particular region of the flow. So this is inclined at an angle theta. So we have this configuration over here, and we have some liquid at a thickness delta, and gravity is acting in this direction, so that the individual components of momentum are going to have gravitational component. We're going to place our coordinate system over here. So this would be x, and this would be our y-axis. Okay, and this plate is moving at a constant, this conveyor belt is a constant velocity of u. So assuming the flow is steady, incompressible, constant properties, etc., etc., it's obvious to you now that this is a one-dimensional flow with the axial velocity component being a function of y only, and you can prove this from continuity, du by dx plus dv by dy plus dw by dz equals 0, since we assumed that v and w equals 0. This implies that du by dx is equal to 0, and this implies that u is a function of y and z. But since we are assuming this is just a there's nothing going on in the z direction, so we're going to neglect this term so that u is only a function of y as expected. Now we have the two components of momentum that matter over here. In this case, I'm not going to directly assume that dp by dx is a constant. I'm actually going to prove it this time, because we expect this to be of the Couette Flow type, okay, subject to a gravitational force. So this would be a combination actually of Couette and Poiseuille flow. Instead of having constant pressure gradient, we have a constant gravitational pull. And so what we expect to have here is velocity profile like this. So this flow is coming up here, and the flow is going down on the other direction. Okay, so the two non-zero components of momentum, after simplification, we have the x component, x momentum, that is going to give us minus dp by dx plus mu d2u by dy squared minus rho g. Now what is the component of g in the x direction? That will be a g sine theta. Okay, so minus rho g sine theta. So if you put g over here, okay, and this would be a theta, so this would be a g sine theta when we project g on the x-axis. Projecting g on the y-axis would give us, so y momentum, we have minus dp by dy minus rho g cosine theta equal to 0. This is equal to 0 over here. Now from this equation we can integrate for the pressure, and so dp by dy equal minus rho g cosine theta. So therefore p is equal minus rho g cosine theta plus some function of x. Okay, so now ask yourself this. P at y equal delta is equal to p atmospheric, which is a constant, and that's equal to minus rho g cosine theta plus f of x. So this implies that f of x is equal to p0 plus rho g cosine theta, sorry, there's a y over here, rho g cosine theta delta. And therefore f of x is a constant. Okay, in other words, the pressure, which is equal to minus rho g cosine theta, now we put the constant back here, we get rho g cosine theta delta minus y plus p0 is a function of y only. So this implies that dp by dx is indeed 0, and we can get rid of this term. So with that being the case, we get our x momentum equation gives us mu d2u by dy squared equal rho g sine theta. So notice how I turned everything into total derivatives, and this means d2u by dy squared is equal to rho g over mu sine theta, and I'm going to call this alpha because it's a constant. A first integration gives us du by dy, it's alpha y plus first constant, and then u of y is equal to alpha over 2 y squared plus c1y plus c2 plus c2. That completes the solution. Next we apply boundary conditions at the bottom of the plate. So at y equal 0, we have u at 0 equal to u, which is the velocity of the belt or of the plate. And if we substitute 0 over here, we get c2, so that gives us c2 equal u, very simply. And at y equal delta, what do we have? We have the shear stresses. The only non-zero shear stresses are tau yx in the liquid is equal to tau yx in the air. Okay? So this implies that mu liquid du by dy at delta is equal to mu air du by dy at delta. Okay? Now this can be taken to be, you could say this is delta minus and delta plus if you want. There's if you want to do that. But the argument here, we've always in the past assumed that just du by dy is equal to 0, but this is actually a more rigorous way to prove this. This is the true condition actually. So this means that du by dy at delta minus is equal to mu air over mu liquid du by dy at delta plus. Now, the problem here is that we don't know the velocity in the air. If we knew the velocity in the air, then we could totally use this. But if you want to approximate this, you could argue that this thing is much smaller than 1 because mu air, the viscosity of air is orders of magnitude smaller than the viscosity of a liquid, and therefore this we can approximate this as being 0. So therefore du by dy at delta equal to 0. So du by dy at delta, that's equal to alpha delta, so alpha y plus c1 at delta, and that's equal to alpha delta plus c1 equal to 0. So that c1 is minus alpha delta, and that completes our solution for the velocity profile. Uy is equal to alpha over 2y squared minus alpha delta plus u, and in a more succinct way, there's a y over here, we get an alpha times alpha y into y over 2 minus delta plus u. That's u at y. Now, the other question to be asked is, obviously, because this profile looks like this, if this is 0, and if you're plotting versus y, this is delta, and this is u. So the velocity here, this is the 0 line. The velocity here is going up, being dragged by the plate, and this is the plate speed. And then over here, this is what you get, and the gradient over here is 0. Gradient over here is 0. By dy is equal to 0. Now there's a point or a condition on alpha or thickness delta for which the flow going up is equal to the flow going down. So the net flow is equal to 0. And this is easily calculated by doing the following. So when is the flow rate 0 flow rate? 0 flow rate. So Q is the integral from 0 to delta phi y dy, and that's equal to the integral from 0 to delta of alpha over 2 y squared minus alpha delta y plus u dy. So that gives us alpha over 6 y cubed minus alpha over 2 delta y squared plus u y between 0 and delta. And that's alpha delta cubed over 6 minus alpha over 2 delta cubed plus u delta. And if we put things together, 1 over 6, and this is, if you multiply by 3, this gives you 3 over 6. So 1 over 6 minus 3 over 6, that's 1 minus, that's minus 2 over 6 alpha delta cubed plus u delta. Okay. Now Q is equal to 0 implies that, so minus 2 over 6 is minus 1 over 3 alpha delta cubed plus u delta equal to 0. So you can find delta, or you can find alpha for which the flow rate is 0. So this implies that, let's say we want to find alpha. 1 over 3 alpha delta squared is equal to u to u, and then alpha is 3u over delta squared. Okay, and that completes the problem.